Okay, good afternoon, everyone. Let's continue on with op amps. So that's the one note. There you go. All right, voltage follower. We stopped right here. So when I was bringing up an example of how we can use the voltage follower to isolate a source from its load, right? So one of the most popular examples I like to use is well, a real life example of, let's say you have a laptop adapter, and your laptop adapter is, well, it's typically rated for like 18 or 19 volts, but just for convenience purposes, let's use 20 volts. So you have a laptop adapter of what? Yeah, yeah. It typically is. If you read it, it would say like 19 volts. And you want to convert that 5 volts, I mean, sorry, that 20 volts to 5 volts, right? So what do you do? What kind of circuit comes to mind? Anyone? The simplest of circuits. Resistor, voltage divider circuit, right? Voltage divider. You were saying? Oh, yeah. The question was, we have our laptops. You have a single voltage coming in and goes into the laptop, but the electronics inside a laptop require multiple different voltages. In a desktop computer, you have a big power supply that has like multiple different output lines coming out. In a laptop, that's not the case. So we have to take the incoming voltage and separate it out, right? So you have a 20-volt line coming into the laptop. Your many of the electronic circuits might require less than 3 volts, like 3.3. Processor might require 3.3 volts. USB ports are standard spec 5 volts. Doesn't matter which USB port you use on any device, it is always spec as 5 volts. So that's the most common example I always like to use. So whether your laptop has 18 volts or 19 volts or 20 volts, doesn't really matter what that voltage is. It's only one single value that's coming into your device. And then it needs to split into multiple different pathways, right? So voltage divider network is the easiest way to obtain, let's say, 5 volts from a 20-volt line, right? So this is where we're applying 20 volts. This is, of course, ground zero. And let's call this point Vx. Now, Vx needs to be 5 volts, exactly 1/4 of your supply voltage. That's why I went with 20. So it's 1/4 of the supply voltage. Resistors need to have a ratio of, well, 3 plus 1 equal to 4. So 3x to 1x, right? So let's keep it simple. Let's say R1 and R2. So R1 value is 3 kilo ohms. R2 is 1 kilo ohm. And you can apply voltage division and you would see that, 20 times 1000 divided by 3 plus 1 would give you 5 volts. So Vx comes out to 5. But now let's say you connect a load that has a resistance of 100 ohms, or let's take extreme example. Let's say it has 10 ohms. All right. So of course this is going to a load, right? It's going to an outlet. And in that USB port, you connect a load that is only 10 ohms. Then what happens then? Let's look at the circuit. You take your Vx and you connect it to a load that is only 10 ohms. Any guesses as to what happens? From 201, what happens? What is the relationship between this 10 ohm load and this 1 kilo ohm resistor? Then parallel. Anytime you have two or more resistors in parallel, the total equivalent resistance is always going to be smaller than the smallest resistor in that circuit. So this parallel combination will have a resistance that is lower than 10. And so, yes, it'll drop. Well, yeah. So the overall voltage here will no longer be 5 volts. It will drop down to, well, let's see, I have it. I'm not going to show the entire calculation. Again, this is just an example. So this total parallel combination, 1 kilo ohm parallel with 10 ohms, comes out to be 9.9 ohms. And then Vx, therefore Vx now comes out to be only 0.06, 0.065. So from instead of 5 volts, now we are getting only 0.06 volts, 60 millivolts. That's basically nothing, right? Almost zero. So our source is basically this circuit, R1 and R2. Our load is the 10 ohm resistor. We need to isolate our source from our load. Do you all see now why I said we always want the load to have a very high input impedance or very high input resistance? So if we split this up and connect a voltage follower between the two, it provides a buffer between the source and the load. The voltage follower, of course, is a unity gain amplifier, meaning whatever input you give at the terminal, you will receive that at the output. So if you now give 5 volts here, you would get 5 volts at the output. But let's analyze this. What is at the what is the input impedance or the input resistance of an op amp? Very high, right? It's infinity. Ideal op amp, it's infinity. In a voltage follower, that still remains the same. Okay, voltage follower, it still remains the same. The input impedance is very, very high. Typically, it's hundreds of mega ohms. Okay, hundreds of mega ohms. Even if you take just 10 mega ohms and you find the equivalent circuit, so you have 10 mega ohms, even the lowest, the very lowest quality op amp will have input impedance that is higher than 100 mega ohms. But even if you take like really the worst one, let's say it has 10 mega ohms and you have 1 kilo ohm here, you apply voltage division, you go through your analysis, and you would still obtain Vx is equal to 5 volts. So 5 volts is going into the op amp here, and you get 5 volts at the output. And now your RL doesn't matter. Your RL could change value to 100 ohms, 1000 ohms, 10 ohms, 1 ohm. It will still get 5 volts supplied by the op amp, because the op amp is always going to take the initial difference, amplify that difference by an infinite amount, send it to the output feeds back into the input, and it instantly drives it back down. And so the cycle keeps on repeating. Again, it's a near instantaneous process, right? It's a near instantaneous process. And so the output will stay steady at like 5 volts. Of course, there are a lot of other components that might go into the circuit. There's circuit protection that we need to do, protect the components from like, extra current that might surge through. But this is the most basic explanation for why a voltage follower circuit would work as a isolation buffer between the source and your load. Does that make sense? Yes.
So why give 5 volts? Even if you why still 5 volts, you have like a figure.
Where? Here or here? I mean, 10 mega ohm? Well, you can calculate the resistance. You calculate the parallel resistance here. It'll be somewhere less than 1 kilo ohm, probably around, let's say 9,990, perhaps. I haven't done this calculation, but it'll be 9,990. You calculate this, it might come out to like 4.98, 4.99. For all intents and purposes, as close to 5 volts as possible. But here I was just saying, even if you take the worst quality op amp, which has a input impedance or resistance of 10 mega ohms, you'd still get close to 5 volts. Obviously, when we are designing a circuit, we would take a look at what that input impedance is, calculate the voltage from here, calculate the exact voltage that is needed. There's lots of other things that go into the operation, right? We could also have a Zener diode in there to keep the output at 5 volts. We might have actually 6 volts coming out to account for like fluctuations and add a Zener diode right there, or like before. So it just depends on what kind of circuit you want and what kind of adapter you want to build. Yeah. Does that make sense on how that voltage follower works as a isolation buffer? Hopefully. Huh? 4.96? 4.996 for, wow, I look at that truck. I literally thought when he drove like this, I literally thought he was gonna come in. Yeah, well, I hope not. Yeah, let's not have any more disruptions, right? Yeah. No, go ahead. Question with this?
Yeah. What happens? Yeah. Maybe if you get off it, like the current, what will be the current going to the feedback?
Where, here right now, or with the resistor or without a resistor? Well, we'll look at it in the next slide. Inverting amplifier, right? Inverting amplifier. This does not have any resistor in the feedback loop. Yeah, that's the difference. So, op amp analysis. Well, first thing we do is we verify what kind of feedback it is, right? Positive feedback, then it's working as an oscillator, working at a different application. Negative feedback, we are forcing the op amp to work in a linear region, and then it can work as an amplifier, right? Otherwise, it will just apply like 1 millivolt and a gain of 100,000, and you have a 10 volt DC supply plus 10 and minus 10. Instantly, your op amp is just going to like 10 volts, right? Saturates. So that's the saturation region for an op amp. In the linear region, we want to work the op amp in the linear region. And that's why we use negative feedback, right? And when we use negative feedback, our inputs will be driven to 0, right? Because it has high input impedance, no current is actually going in. So the current going into the op amp, In is equal to 0. And because we are applying negative feedback, we are forcing the negative terminal to go exactly the same value as our positive terminal, meaning V1 and V2, or V plus and V minus, are exactly the same. So the input voltage going into the op amp is also 0. Okay, so we have to verify first negative feedback. Once we verify that it has negative feedback, then we can assume V in and I in are 0. And after that, we can apply any analysis technique we want. Basically, KVL, KCL, nodal, Ohm's law, any analysis technique we want to solve for the currents and the voltages. Okay, so negative feedback is if there is a resistor connected there. It's V out. It could be an inverting or it could be a non-inverting amplifier. Does not matter. I'm going to leave that open right now. You have a resistor here in the input path. That's how it's configured. This is called RI. This is called RF. V inverting. Well, sometimes I tend to use V1 and V2, but some problems use V1 and V2 for other voltage supplies. So let's use V minus and V plus. Some books, so inverting terminal voltages are referred to with the notation of minus or N, and non-inverting are referred to with the notation of plus or P. Okay, plus or P. And Vin is the input going into the op amp, would be V plus minus Vin. Okay, V plus minus Vin. Obviously, if V plus and Vin going into the op amp are exactly the same, that won't be amplified, it's rejected. Only the difference between the two is amplified and sent to the output. Right? Again, remember, op amp at its most fundamental, at its most basic, is simply a differential amplifier. It simply amplifies the difference. So the difference can be very, very small, but if it's 0, then it won't be amplified. It'll just be rejected. Okay. All right. Questions? Any questions before we move on to our first derivation? Inverting amplifier. Oh, I do want to point out, I realized there was some confusion last class, but as I mentioned now, the first thing to do is verify negative feedback. Without negative feedback, we cannot assume Vin is equal to 0. Okay, we cannot assume Vin is equal to 0. So negative feedback is what forces that terminal input voltage to go to 0, because we are taking an output, and instead of the in the voltage follower there's no resistor. Here we have a resistor, so we are taking a fraction of the output and feeding it back into the input, because the output would technically be infinite. For one instant it will be infinite, limited by the power supply constraints, goes back into the input. That is cancelled out with whatever we have at V plus, and that's why we can assume that both V plus and V minus are at the exact same potential. That was the virtual short concept that I was talking about, right? V plus is equal to V minus. Yes. Well, if we see a connection going from the output back to the negative terminal. No, not quantity. It's just visual inspection. We take a look at it and see. Yeah. Oh, it's basically, sometimes it's easy to miss because the minus and the plus signs, if it's not, if it's very small image, it's a little difficult to see, but that's what it's just saying. Verifying negative feedback means visual inspection. Take a look at the circuit and then see if it's going back into the negative terminal. So, inverting amplifier, so called because the input signal is connected to the inverting terminal of the amplifier. Okay. Now, here we have two resistors, R1 and R2. We take a look at the output and we see R2 is connected back to the inverting terminal. So we do have negative feedback. Okay, we do have negative feedback. Oftentimes, R1 in some books will be labeled as Ri or Rin. And R2 will be labeled as Rf, F signifying feedback. Okay, so Ri or Rin and Rf. Now, current direction. We see that this non-inverting terminal is connected to ground. So potential here would be 0 volts. So first thing is, of course, we verify negative feedback, and if negative feedback is present, then we can assume that both terminals have the same voltage, since V plus is equal to 0 volts we can write V minus is also 0 volts. And therefore, Vs, sorry, not Vs, Vx, the voltage going into the op amp is also 0. No difference. Yes, ideal op amp. Yep. And so now let's write down our currents, right? We'll have V in will have some value. It'll supply some current right there. We'll call that I1. We can call this I plus or IN, but, oh, sorry, not I plus, I minus. It's a negative terminal current going in, and this will be I2. If we say that the op amp has infinite impedance, the second step or assumption is that the input current also is equal to 0. So if the input current is 0, I1 is equal to I2. Everything's going on this direction, right? And then it goes here. So now VO is right there. So the voltage at this point, let's call that V minus. Voltage at this point, let's call it V plus. Right, and we have VO. If we remove the op amp, from our circuit right here, let's say there's no component and we just think in terms of resistors and nodes. What do we have? We apply KCL at this node, we get I1 is equal to I2. When we want to express, think back to node voltage analysis, we want to express I1 in terms of the resistor current, in terms of the resistor voltage, VR1. The resistor voltage across VR1 can be expressed in terms of the node voltages at either end of that resistor. And which direction is the current going? Which point is higher? So V in minus V minus divided by R1 gives us I1. Does that make sense? How about I2? Forget the op amp. The voltage here is VO, and here it's 0, absolutely. V minus is 0. So now we have 0 minus VO divided by R2. We take that and we equate it to this equation right here. So now in our equation, we have both V in and V out. We rearrange the terms and we can get an expression for V out is equal to whatever. And then to get the voltage gain, we do V out over V in. And we get the gain, AV. Right? Yes.
So do you feel that V out will the local impedance, we reflect V out to negative?
Yes, we connect it to negative right there. There is some flow that's actually going in the opposite direction, and you will see when we actually apply, the answer comes out to be minus. The analysis reference is always taken like this, because we also, yeah, the answer comes out to be negative. And then again, it's because an inverting amplifier, right? So that's what the negative sign will imply. Yeah. So if you apply KCL, actually, let's start from here because it's not enough space there. Apply KCL at inverting input. And I can write I1 is equal to I2. I1 can be described in terms of the node voltages. So V in minus V minus divided by R1. And here it would be V minus minus VO by R2. We rearrange the terms. And we should get Let's see. V in minus 0 or R1 is equal to minus VO or R2. Therefore, V0, sorry, not 0. This is VO. This morning's class, I was doing a lot of zeros. This is O, not 0. So VO is the input voltage minus input voltage times R2 over R1. That is the equation for the output voltage. And my gain, AV, voltage gain AV, which is given by VO over Vin, is minus R2 over R1. You can also solve this by applying KVL. So if you solve this by KVL, let's write it down and then I'll talk about it. So again, it does not matter which analysis technique you take, you will have the end, the end result will be the same. Actually, let me write it on the side. So here, if I was to draw so this is VO, this is R2 plus minus VR2. This is virtual ground. And so I can literally state this is connected here. So if I apply KVL around the loop, I get VO equal to minus VR2. VO is minus VR2. It's simply minus I2 times R2. I2 can be written as minus V in over R1. And so we get the exact same equation. VO, again, I did a 0. VO is equal to minus V in into R2 or R1. So you can apply KCL and solve it. You can apply KVL and also solve it. All right, questions?
In that case, so the training is going to look like on the opposite direction.
Yeah.
That's how
Even at the output. So when we teach when I do the same for E major class, we use a different textbook. So that textbook uses, we look at 5 currents. We look at the 2 currents going in, so inverting terminal, non-inverting terminal, and then we have the plus positive supply coming up top, negative supply coming from the bottom. So both those currents are going into the op amp. Then we have the output current, and the output current is not going out, it's actually going into the op amp. So different textbook, different convention, but the end result is the same. So again, that's an E major class that I teach. That's the yes. Yes.
So when they meet at the node where negative VI, where does that come from?
So right here. Right here. So it's not going into the op amp. So we say I negative is 0, And so we can say I1 is equal to I2. So again, we are analyzing ideal op amp. We're saying absolutely no current is going into the op amp. And that's how we can make an assumption that I1 is equal to I2 at that node. So we're applying KCL at this node. If you apply KCL, we would get I1 is equal to I minus plus I2, but I minus is equal to 0 because no current goes into the op amp. So they yeah, in that. I keep brushing up over here. Yes. So it also depends on the configuration of the circuit and also the values of the resistor. But for the most part, yes. Yeah. I know it's not an easy concept to grasp right at the beginning. It does require a lot of detailed analysis in the explanation. Other questions? Okay. In real life op amps, there is actually some current that goes in, okay, into the op amp. So that's again a different consideration. So this is again assuming it's ideal. So ideal op amps, we make assumptions. Real op amps, there is current that's actually going in. But most of the current that is required for the operation of the op amp comes from the power supply, which of course we don't show. The plus VCC and minus VCC. That's where most of the current comes from, right? The actual source current is going to be very, very small. And the op amp does a really good job by having high input impedance and does a good job of not loading whatever quantity we want to measure. Other questions? Other questions? Okay, then let's look at an extension of the inverting amplifier. We call this a summing amplifier. A summing amplifier. So this example here uses only 3 inputs. I'm going to go ahead and add a third one. And let me go. Let's call this VC and RC. Okay, VC and RC. This is feedback resistance RF, current IF, current IA, IB, and IC. As usual, first thing we verify is negative feedback. We see that the output is connected back to the inverting terminal, so negative feedback. If negative feedback is there, we can assume the differential voltage going into the op amp is equal to 0, meaning a virtual short, meaning the non-inverting terminal grounded is also grounding, well, not grounding, but keeping the inverting terminal at 0 volts. Okay, 0 volts. Okay, so we follow the same analysis technique that we used earlier. We'll apply KCL at the inverting terminal, sum up all the 3 currents, and all those 3 currents will equal IF. IF. We express each of these currents in terms of the node voltages across the resistors, and we can write IA is simply going to be VA over RA. IB is going to be VB over RB. Well, it's VA minus the inverting terminal, which is 0. I'm just omitting that 0. You got VC over RC is equal to, this is now 0 minus V out divided by RF. So V out or VO is equal to minus RF over RA times VA. Oh, actually, that minus sign is outside, so let's keep it outside. Plus RF over RB plus, not plus, times VB plus RF over RC times VC. If we choose RA equal RB equal RC equal a single value R in, we can write the expression for VO as minus RF over R in times VA plus VB plus VC. So a summation of the inputs and inverting amplification. VA plus VB plus VC. If we wish individual gain, then we change the values of RA, RB, and RC according to what we want. And we can change the gain of the input separately. Okay, so that's how this works as a summation amplifier. You simply just connect 2 or more inputs at that terminal, and it would work as a summing amplifier. That's actually one of the earliest uses of op-amps. They were used for summation of signals. Okay, so summing up signals, addition, subtraction, integration, differentiation. That's why the name operational amplifier, that's where it came from, right? It was used to perform a variety of operations. Analog computers were built using op-amps, and the name has just, stuck ever since. We just use op-amps for short. All right, questions? Any questions at all? Yes.
So all these photos will have a feedback, no?
Negative feedback, yes. Yeah, we'll only look at circuits with negative feedback. We won't look at oscillators and stuff like that. Not enough. It's in a quarter system. There's not enough time to actually look at all of those things. Yes.
So this could be inverting amplifier, the inverting input is actually speaking to that ground.
Where?
The inverting input or
Non-inverting input. Oh, you're talking about here? Yeah, it's just the potential at both is 0 volts.
so it's like ground.
Yeah,
So
you want to say ground.
replace it with the ground, wouldn't it be the same thing? You just replace it with the ground, wouldn't it be the same thing?
Well, if you replace it with a ground, all of the current might just go through there. It won't go through the feedback resistance. Again, we assume virtual short for the purposes of analysis. So we can say that the current from there is actually going into, into the feedback path. Here? Here? No, that was the original question. Can we actually ground this? The answer is no. If you ground this, then everything would just, there will become a path that goes directly in there. IF would just remain 0. So physically grounding it would not work. Then the circuit will not work as intended. That would come in this non-inverting amplifier, where we are actually grounding the inverting terminal and giving the input to the non-inverting terminal. So that's, sorry, what? Actually, not really. I'll redraw that circuit. So no, the answer is no, you can't actually connect it to ground. If you connect it to ground, then current has a pathway to actually just flow through there, and the feedback path would just be useless in that sense.
Where the operational amplifier, so the current still can go out in there.
Yes.
Oh, you can even replace that with a, oh, never mind. Thank you.
Okay, non-inverting amplifier. Now, I'm usually not a big fan of switching things around like this. So the circuit diagram I prefer to use is this. Let's hold off. We still have all right. So the negative terminal is still on top. We got R1 and R2, except this time we ground R1 and we apply the input to the non-inverting terminal. Okay, non-inverting terminal. The analysis for this, we still use the same convention, but this case, makes it easier. Okay, so we have Vn, let's see, V1, VO. If you take a look at the circuit at the top, just the resistors without the op amp, what do we see? R1 and R2 is in series. We have VO or V out. We still have, well, we'll still assume the current going in this direction. Right now, we'll just apply KVL in that loop. If you apply KVL in that loop, how much time do I have? 153, plenty of time. So V out, R2 and R1, voltage divider network, right? Voltage divider network. So what is the voltage across V1? What is the voltage across, sorry, not V1, across R1? So you have R2, R1, and voltage across V1 is, so this is VO. You got R2 and you got R1 connected to ground, voltage divider network, right? What do we get? V1 is equal to VO times the resistor of interest, which is R1 divided by R1 plus R2. And now here's the confusing part. You're applying input voltage at the non-inverting terminal, right? But we have negative feedback, right? From the output, it's going into the negative terminal. So you have negative feedback, then we say there's a virtual short at the two terminals. So both terminals, input terminals, the voltages have to be equal or have to remain the same. So we can write that V in is equal to V1. V in would go equal to V1. Okay. And if V in is equal to V1, we plug the above equation right there. R1 over R1 plus R2. We rearrange the terms and we get VO as equal to V in times R1 plus R2 divided by R1. And we get VO is equal to V in times 1 plus R2 or R1. And therefore, the gain, the voltage gain of the circuit, which is VO over V in, is equal to 1 plus R2 over R1. Yeah. Well, you think about it, it's negative feedback, right? So fraction of the output is going into the input, right? Fraction of the output is going into the input. And so that's why VO times R1 over R2, R1 over R2 plus R2. Anyway, that's the derivation. Now, as usual, if you've been in my class before, you know I don't harp on derivation a lot as long as students understand what the equations are and how to use them, right? So if you have an inverting amplifier, you should be able to recognize an inverting amplifier. You should be able to recognize a non-inverting amplifier or a summing amplifier. If you want to find currents through any of the resistors or the voltages across the resistors, you should be able to apply the basic KCL techniques, which I have 3 minutes. So I'll do an example in that time. So you should be able to apply simple analysis technique and be able to determine what the currents and the voltages are for those resistors. If we are given a value, let's say you're provided a circuit with different resistor values, you should be able to calculate the gain or the output by applying these equations. And since if R2 is 10 kilo ohm and R1 is 1 kilo ohm, gain is 1 plus 10 equal to 11. And you should be able to calculate the output based on that. Rather straightforward. There's nothing too complicated about it in that sense, right? I'm not going to ask you to sit there and like derive a bunch of equations from just the circuits. Especially as non-EE majors, it's more important for you to realize how you can take these components and well use them in a larger circuit or a larger device, right? Make sense? So there's an example for a non-inverting inverting amplifier. Let's go ahead and do that in the few minutes we have left. And we are given what are we given? Let's see. In that example, okay, I1, I2, this is given as 10K, this is given as 1K, negative, positive, ground, IX, and IO. And this example is where you'll be able to see the actual negative value for the currents. So let's see. RL is given as 1 kilo ohm. And you're applying V in of 1 volt. So V plus is 0 volts, so V minus, is also 0 volts. So therefore, I1 would be 1 minus 0 divided by 1K, which is 1000. So it's 1 milliamp, right? From our assumption, from our assumptions, we know I1 and I2 are the same. It's also 1 milliamp. And then, let's see. I2 can be described as 0 minus VO divided by 10,000. Therefore, VO is minus 10 volts. And from there, I can find IO. IO is minus 10 volts divided by 1,000. So minus 10 milliamps. And apply KCL, I can find IX. IX would be IX plus I2 is equal to IO. Therefore, IX is equal to minus 10 minus 1 minus 11 milliamps. And so IO and IX both have a negative value, seemingly going into the op-amp. Okay. All right, we went 1 minute over time. Hopefully the examples make sense. Op-amp fundamentals homework is due tomorrow. I think there's just a few questions in there. There's extra credit, which goes much beyond than what we can do in the classroom. So if you are, if you wish, you can do the extra credit problems. You can learn about a little bit more than what we do in the classroom. That's for extra credit tutorial, and it's optional. There will be a quiz on Monday. I will send an yes. So there's another homework due on Sunday. I will push it back to, well, push it back by a couple of days at least.
Sunday is the op-amp for the campus. The other one is tomorrow. That's the DJT part of it. Yeah.
Oh, okay. So 4 resistor homework due tomorrow, and then op-amp fundamentals is due on Sunday. Okay. So the 4 resistor is something we finished up on Monday and Wednesday. That's why, and then I pushed it back over the weekend. So if it seems it's close together, it's just because I pushed it back. So fundamentals, again, as I said, it's not going to take too long. I'll still push it back, but you should get started on learning from that homework. I will be available all weekend. I don't have any big plans for the big game. I'm just gonna watch. So if you need to see me over Zoom or email, just send me an email and I'd be happy to see you. Yes.